Hi, I'm Susanna and I'm presenting the work of logical satisfiability of counterfactuals for faithful explanations in NLI. So this work primarily presents a new methodology on using logic to evaluate generative explanation faithfulness. The TLDR is to rewrite a natural language explanation into a counterfactual hypothesis and then check if the new hypothesis is still logically satisfiable. So first, let's start with some motivation. Everybody wants to generate faithful explanations. Evaluating an explanation's faithfulness is desired for many reasons such as trust, interpretability, and diagnosing the sources of the model's errors. But what are explanations and where do they come from? What do we mean by faithfulness? What is the problem with the existing paradigm and the current measures such that we need to partake on this project? So intuitively, we would like the provided explanation to reflect the true reasoning process of the model when making a decision. Now, this is impossible to fully satisfy. If you have a separate model, black box neural network, and it is pretty much impossible exactly to say what is happening. And most of the time, we are just probing for interpretations, right? Even if you try to explain what's going on in your own brain, it will not be an exact reasoning process. Instead, faithful measures should focus on the utility to the user and the idea that an explanation can be sufficiently faithful. Okay, so where do explanations come from? Explanations are typically categorized into free-form, generative, and extractive rationales. And we deal with free-form natural language explanations in this work. The classification task in question is multimodal NLI, and the standard thing that people do in this task is to fine-tune a language model to generate the free-form natural language explanations using inputs and predicted labels from the multimodal task itself. So our setting is characterized by the interpretation of black box classification models via generative explanations, and this is known as the predict and explain paradigm. Now, given an image as a premise and the text as a hypothesis, the possible labels are the entailment, contradiction, and neutral of the premise and hypothesis. Here we have an example of visual NLI. The premise is the image you see here, and the hypothesis is that the people are standing around at a beach, with the correct label being a contradiction. The natural language explanation that has been crowdsourced for why this is a contradiction is that the construction site is different from the beach. So this was a data set that was gathered in 2020. The problem with this existing multimodal explainability paradigm is that the modeling is post hoc and disjoint. It's post hoc and disjoint because first, we have a multimodal model F, which can be united or clipped, so any kind of multimodal model, which then learns a joint representation of image and text and fine-tunes a linear task layer to predict the answer. Then, to generate explanations, a separate language model conditionally generates the explanation using the question, multimodal embedding, and task answers as the input. The problem with this is that there is no way to check if the explanations themselves reflect the reasoning process of the upstream model when making a decision, and it's subject to label leakage or artifacts which are correlating the task label and the explanation text training data. So these are actually two separate models. Now, if we look at what people have done previously, we find that there is some issue with the method in that either they do not test the model directly or they require a third-party verification model, which again raises the question of faithfulness to the original task model, or that they assume that the explanations are going to be available together with the task model at training time. So we reviewed 4 pretty well-known approaches, and we find that all of them have at least two or three of these problems. We would like instead to propose a method that tests the model directly. It does not rely on third-party verification, and it does not assume that you can train with explanations at training time. So, for example, I can give the model a human explanation and check if the model is consistent with my human explanation. Okay, So moving on to the main idea or intuition of the approach, explanations should be logically consistent with the model's original predictions. So given the model prediction, say a model F is applied to a hypothesis containing A, which results in a contradiction. And the explanation given for this is that this is a contradiction because A is not B, or A and not B. Then we consider that this explanation is satisfiable if the model F applied to the hypothesis which contains B instead of A now results in an entailment. Okay, so the methodology consists of first applying logic to derive what the new label should be, and second, generating the new hypothesis automatically. Okay, so the core idea was rewriting hypotheses based on propositional logic. So why is this interesting at all? Let's see an example when the explanation is sensible but actually not faithful to the model. So in this image, if the original hypothesis is that the woman is standing on a snake, is a contradiction, and the explanation given is standing on a snake is not the same as sitting on a fake alligator, we can rewrite this in logical form and then construct a new counterfactual hypothesis to be the woman is sitting on a fake alligator. Now we know that the logical consistent label should be an entailment. Yeah, so we write the new hypothesis and we know that the logically consistent label should be an entailment. But instead, if the model now predicts a contradiction instead of an entailment, then even though the explanation sounds kind of correct, it is not a faithful explanation to the model. Another reason why this explanation could be wrong is that the girl is not a woman. So we are essentially testing if whatever the explanation is written, is it consistent with what the model is predicting? Okay, to recap, we want to first revise the input text hypothesis according to the relations expressed in the natural language explanation. And second, derive the logical label for this new counterfactual hypothesis. So we have derived the logical labels for the three NLI classes of entailment, contradiction, and neutral, the details of which are in the paper. So I'd like to mention that the derivation of contradiction and entailment is very straightforward. The neutral label is more interesting because it doesn't fall directly under propositional logics, which is binary valued, true and false. Instead, it falls under something called free logic, where neutral itself is true valueless. So neutral means you neither know whether it's true or false. And in order to evaluate neutral, we need to test two counterfactual hypotheses instead of just one. Right, so going back to the main idea. We know how to apply logic to derive the new label, but how do we generate the new counterfactual hypothesis? So this is the process. Given an explanation, we want to first extract spans corresponding to logical variables A and B. For instance, standing on a snake is not the same as sitting on a fake alligator, is the explanation. We would then extract standing on a snake as variable A and sitting on a fake alligator as variable B or text span B. Now, given the original hypothesis, the woman is standing on a snake. We would then transform this into a counterfactual hypothesis by rewriting the span corresponding to A into the span corresponding to B. So then we will end up with the woman is sitting on a fake alligator. And this is the process for just contradiction. There is a different process for entailment and neutral. Okay, so experiments, I've finished the core idea of the approach. Now I'm moving on to experiments which validate whether this idea actually makes sense or whether it actually works. Okay, so we validate the method through three sets of experiments. The first is to evaluate the quality of the generated hypothesis using a few shot generators. So just given a few examples of how to do the extract and transform step, which I just showed, how well can GPT do this? And it's a small GPT, it's not like the 175 billion one. Next, we want to evaluate the proposed metric on GOAT model agreement of human-generated counterfactual hypothesis and compare this to existing faithfulness metrics. Next, we also have a sensitivity analysis of our proposed approach compared to other metrics given pathological explanations. So we intentionally make the explanation pathological and see whether different measures actually report that the faithfulness decreases. Okay, so first, the quality of generated counterfactual hypothesis. The research question here is, can the automatic method actually generate counterfactual hypotheses for different types of explanations? The hypothesis generator we use here is a GPT-Neo 2.7 billion parameter, which is a completely open source. You can get it from Hugging Face. And the eval metric used here is Meteor score, which is word overlap and synonym similarity scoring against human-generated counterfactual hypothesis. So what we see here is that the combination of using models for both extract and transform step, which is the last row, performs best in all cases with the human explanations. And we also see in the paper that it performs very well with model explanations. So the performance of most methods are good on generated human explanations, which might be explained by the very standardized text format in the generated explanations. The row regex can be seen as a direct comparison of how standardized the explanation is compared to how standardized the explanation is. So you see in neutral that it's very unstandardized, so you can't really find a good regex pattern for it. Okay. Next, we try to validate the metric on gold model agreement of human-generated counterfactual hypothesis. As we mentioned right at the beginning, one practical utility is that humans should have a better handle of the model's predictions if we get slightly different input. So the domain of slightly different input that we test is now going to be the counterfactual hypothesis that has been generated by humans themselves. So faithfulness metrics should be good at discriminating whether these gold predictions agree with the model's predictions. So can our proposed metrics differentiate in cases where the human agrees versus disagrees with the model? And the baseline metrics we compare against and we implement and compare against are LRA and LAS, which is some previous faithfulness measures. Just in quick summary, we are using a Wilcoxon rank sum test, which is score from 0 to 1 between two groups. The higher, the better. So the two groups are human agrees or doesn't agree with the model prediction, and a star indicates significance. So FTC is our metric, and we see that it mostly is significant in separating these two groups. Okay, I will skip the last experiment on sensitivity analysis and go straight to the conclusion. So the strength of this work is that it fills a gap with previous faithfulness measures, right? Because previously we are subject to things like label leakage, third-party reliance on third-party verification, and we sidestep all of this by simply generating counterfactual hypotheses and then applying these logical satisfiability checks. We also introduce free logic to handle the neutral label, which hasn't been mentioned in the literature before. And moving on to some pretty important weaknesses or limitations of this approach as well, is that we can only say for sure when an explanation is not faithful. So if it is not consistent, it is surely not faithful. But even if an explanation is consistent, it does not mean that it is certainly faithful, right? To look at it very strictly, there could be other reasons why things turn out to be logically consistent. It could just be by chance or some other artifacts in the data. The second weakness is that while most classification problems can be reformulated into true, false, neutral, or entailment, contradiction, neutral, it is an open question of how to extend this notion of satisfiability for open-ended text generation. So essentially, we relied on being able to derive a logically correct label, but you can't always do that if the task is generative, like machine translation or summarization. So there is no correct explanation for why a model generates a particular summary. So we made some progress towards the notion of faithfulness. I think we are a step closer towards the notion of faithfulness, but we certainly haven't solved what this actually means. And in future work, there should be more nuanced and practical formulations of how to test for this. Okay, thank you for listening to my talk. Okay. Start recording.